today is open your Chromebooks. We're going to kind of prep these together, let you have a chance to answer questions together, ask questions. I think this is 6C15. We're looking at 6C15, yes? 6C15. It's important that we learn what things you can do to engage in class. Let's ask questions today, if you have any. Let's answer questions if you're able. Getting involved is a way to help yourself learn more, stay awake, engage in learning, be an active learner. Become an inspired learner. All right, here we go. Let's take a look at these. We are trying to decide what is the dominant type of intermolecular force that the molecules can exhibit. We've got a couple choices here. We've got London dispersion, dipole, and hydrogen bonding. How do we know if it's hydrogen bonding? What must be on the molecule for it to be hydrogen bonding? Yes, we have to have a hydrogen, and that hydrogen has to be attached to a what? Yes, a fluorine, an oxygen, or a nitrogen. Well done. Very well done. Yes. Why can't it be fluorine? That's a great question. It's an outstanding question. Question is, why couldn't it be chlorine? Because nitrogen is 3O, nitrogen's 3,5, fluorine is 4O. Those are the three highest. But chlorine also is 3O. Chlorine, like nitrogen, is 3O. So why couldn't it be chlorine? Anyone? What's smaller? Nitrogen is smaller. Didn't you? Yeah, yes. Nitrogen smaller. What does the size matter for the strength of the dipole? Because hydrogen bonding is really a special dipole that falls into its own category because of how strong it is. Why does the size of the atom influence the strength of a dipole? The smaller the atom, the stronger the dipole. Why? Smaller space, that force is more concentrated. When you have a larger atom, that dipole strength is being spread out. Sort of like if we have a large bucket of water and we put in 1 drop of food coloring, we're not going to see it. It gets spread out. We would barely even notice. But if we have a thimble full of water and we put a drop in, you're going to see the color. You're going to see the food color. So here, nitrogen is small. So that dipole is concentrated in a smaller space, making it an overall stronger force. So that's what we're looking for hydrogen bonding. Let's see if we can right away find that one. Does this molecule here even have hydrogens? No, it can't be that one. This one does have hydrogens, but what are they on? They're on a silicone. Hydrogen's actually a higher electronegativity than the silicone. Is there a hydrogen on this one? No. Is there a hydrogen here? Is it on a fluorine? Yes, that's hydrogen bonding. Letter C. We're only allowed to use the answers twice, so let's hope that there's another one that has a hydrogen on an oxygen or a nitrogen. Let's hope. Is there? Are these hydrogens on an oxygen, a fluorine, or a nitrogen? No. This one? Yes, that's hydrogen bonding. Hydrogen bonding. So we've got those. Now, what about, how can we tell if it's dipole-dipole? Dipole means that the molecule has a net dipole. It has partial positive areas and partial negative areas. That's what it means. That means they will stick together because of the dipoles. There will be an attraction between nearby molecules. London dispersion forces. Dipole-dipole are polar molecules. To be a polar molecule and have this net dipole, two conditions must be met. It must be, thank you, it must be asymmetrically shaped. In other words, a lone pair of electrons on the central atom that will bend the molecule so it's no longer symmetrical. What's the other factor? Electronegativity difference enough so that it is greater than and equal to 0.4 in this class, which would give the bonds what? Polar or nonpolar? Polar. Remember the shape sheet. Do you remember the 6C10 where you went through and you're like, if it was asymmetrical and had polar bonds, it took you straight over to polar molecule. London dispersion forces then are opposite this kind of thing. They are going to be symmetrical and or have nonpolar covalent bonds. Nonpolar covalent bonds. What are London dispersion forces? How are they different? Yes, molecules can attract each other. Molecules can attract each other with London. London is generally considered to be a lesser attraction than a dipole because it's not a partial charge. It's a temporary, momentary attraction. That results from what? You were going to help me with that one, yes? Shifting of electrons to different parts of an atom, not from one atom to another atom, but they shift on an individual atom, creating a little temporary positive place and a little temporary negative place on the atom because the electrons are moving. So what happens to the strength of London forces? If we're shifting electrons on an atom, if we have an atom and the electrons shift to this side, it's going to make this side feel negative. It's going to make the side they left the atom feel positive. So if there's another atom nearby, if I have another atom nearby, if this side of this atom is positive for a little bit, what's it going to do to the electrons on this atom? They'll attract over, and we will get this attraction between the molecules. These can come right back. These electrons can drift right back, but what would it do to these electrons? Push them away. A dipole is there, and it's not going anywhere. When we have a dipole attraction, it's not going anywhere. It will always be there. As long as that molecule doesn't engage in a chemical reaction and end up with different atoms in different places, it will always be there. The London can keep shifting. The partial negative, or the side that's positive can become negative, causing the side that's negative here to become positive. That doesn't happen with the dipole. Dipoles do not flip. But what would make London stronger? With a dipole, we are looking for big differences in electronegativity. That makes it stronger. With a dipole, dipoles get stronger when we have a big difference in electronegativity and we have small atoms. Yes? Because it's concentrated. And the stronger they're pulling the electrons to them, the stronger the dipole is. Is that true of London? If I have electrons shifting, wouldn't it help if there were more electrons that could shift? Yes. What has more electrons, small atoms or bigger atoms? Larger atoms. What else? If the atom, in order for electrons to sit there and freely move on the atom, can the atom hold the electrons tightly? No. If an atom is pulling on its electrons tightly, higher electronegativity, higher ionization energy, the electrons are not free to drift about. So with the London dispersion force, they tend to be stronger on larger atoms because there's more electrons and weaker ones, so that they're free to move around. Lower electronegativity. London is almost directly opposite the dipole-dipole. So to tell if it's London or if it's dipole-dipole, we merely need to look what kind of bonds are on the molecule and is it symmetrical or asymmetrical. Here is where using tricks can speed it up a lot. We already did number 2. Sulfur dioxide. Sulfur dioxide. Oxygen prefers 2 bonds, yes? Oxygen prefers 2 bonds, double bonds. Sulfur starts with 6. We've got 2 oxygens preferring double bonds. This is a little trick if you were in a rush. So there's going to be 4 bonds. That would leave us a lone pair of electrons on the central atom. Did you see that little trick? This is if you were in a rush. If you're sitting in a college chemistry class and they're like, pencils down in 3, 2, and you're like, oh my gosh, I've got 1 second to answer this on an exam. You could be like, sulfur starts with 6, oxygen prefers 2 bonds, there's 1 oxygen, there's another oxygen, there's a lone pair. Oxygen with anything is going to be polar. That will be dipole-dipole. Now, if you have more time, draw it out following the Lewis rules. We have 18 electrons, sulfur's in the middle, surrounded with 8. Attach the 2 oxygens on either end, you surround them with 8. Did anybody have trouble drawing this one and wants to see it? I am happy to draw it. Why? Because I love drawing. I'm an artist at heart. I was 4 years away from being an art major in college. Had I gone for 4 more years, I would have been a dual major in art. Yeah. Assuming I would have been accepted to art school, which probably may have not been the case. We continue on. What about number 3? How do I know I could do number 3 without really even drawing it? If I was in a rush. Silicone starts with how many electrons? It's Roman 4. It starts with 4. How many bonds does hydrogen prefer? 1. It only has 1 electron. 4 minus 4 is what? 0. There's no lone pairs. It's going to be symmetrical. It's going to be symmetrical without even drawing it. If I was in a rush. If it's symmetrical, I don't even have to check the types of bonds, polar or nonpolar. Wouldn't even need to do it. You have to have that lone pair on the central atom. Would the London forces on this molecule be very strong or very weak to the point of being about as weak as you could get? Why do you say weak? Who's in here? Hydrogens? Are terminal atoms hydrogens here, yes? Are hydrogens polarizable? Referring to making the atom have little areas that are negative and positive. How many electrons does hydrogen have? 1, and it's in a bond. There are no other electrons on the hydrogen to push around. That is a really small atom, not polarizable. London dispersion forces would be very close to being non-existent on that molecule. What about this one? How could I do this one if I was in absolute rush? Yes. Oh, well, let's say I look at the clock and I've got 10 seconds left to answer this question. I probably couldn't draw this in 10 seconds. And I'm trying to decide, is it London? I already used the hydrogen bonding. I already used the hydrogen bondings. That answer was used. I've used one of the Londons. So I have another London, and I've got 2 dipoles left as my answers. Does everybody see where I'm getting this? I'm seconds away from finishing this test. You don't, when they say pencils down, you put your pencil down. Yes. Sulfur starts with 6. Oxygen prefers 2 bonds. How many oxygens are on there? 3. 3 times 2 is 6. There's going to be no lone pairs left on the sulfur. I could mark, I mean, if ultimately they're looking to see what answer you put here, you could do it. Now, that trick works when the molecule is not charged. Because if the molecule's charged, oxygens wouldn't have to make 2 bonds. Because if the molecule's minus, the oxygen had made a previous bond that broke. Are you following me? That trick does not work if the molecule's charged. You can still use the trick, you just have to adjust it. So, if I only had a few seconds left on the test, I would already know the answer to the last number 6, because the only answer I have left is what? What? I have a B left, because we're only using each answer twice. How would I know? How would I know that this molecule likely is a polar molecule with a net dipole? They told us the oxygen's where? Between the 2 carbons. So that means I would really just need to draw this part of the molecule. They told you oxygen's between the 2 carbons. So I have a carbon on one side, the carbon on the other. If you ask oxygen what the shape of the molecule is, oxygen starts with 6 electrons. I have 2 carbons on it. That is 4 electrons left, or 2 pairs. They told you the hydrogens were on the carbons, didn't they? The hydrogens, the 3 hydrogens are on each of the carbons. So the carbon could have only made a single bond to the oxygen, because carbon can only make 4 bonds. It has 4 electrons. 3 of them are to the hydrogens. That means it can only make 1 bond to the oxygen. That's all it could do. So there's 2 carbons making 1 bond onto the oxygen. That leaves 2 lone pairs on the oxygen. 2 lone pairs immediately. That molecule is asymmetrical. Oxygen and anything other than another oxygen's polar bond or ionic. Oxygen can't share nicely. If you want to share nicely with somebody, don't ask oxygen. Because oxygen will either just take what you thought you were going to share and go ionic, or it's going to hog everything. Oxygen's a bully. I'm just telling you. Wake up. In life, there are bullies. If you ask oxygen what the shape of the molecule is, what would oxygen say? Is oxygen bonded to 2 atoms? Are there 2 lone pairs? B2E2 is what? Angular or bent. Very good. B2E2 is angular or bent. We've done that one enough that you shouldn't have to look. If you ask carbon what the shape of the molecule is, what would carbon say? If you text carbon, you're like, what's the shape of your molecule? What would carbon say? Square planar, you would have to be AB2E2. Are there any lone pairs on carbon? No. 3 atoms. AB4E0 or AB4 is tetrahedral. Tetrahedral. All right, that's 1 through 4. And that's all we'll have time to go over for today. So if you had any other questions, too bad for you. Oh, wait, what time are we out? All right, we've got some time. How are we doing on number 7? Question on number 7. You're like, where did we get that? Well, we already know that has already boiled. That has already boiled. This one hasn't boiled, and this one is a solid. Gas, gas, liquid, solid. They want it in increasing boiling point. Increasing boiling point means lowest IMF first, highest IMF last. The higher your boiling points and melting points, the more strongly your molecules are held together. What kind of force is it that's holding these together? Is it ionic? I know, no metal. Yes? London. Don't have to draw it. You have two of the same atoms. That automatically symmetrical. If you two have the same atoms, the electronegativity difference is 0. So we're looking at London. London forces increase with an increase in size. So we want the biggest atom last, the smallest atom first. Fluorine has really low polarizability. Question on number 8? Or did we just answer number 8? Just answered it? How are we doing on number 9 or 10? Today's your day to ask questions. Yes. Number 9. Higher vapor pressure. That means we are looking for the one that goes to a vapor easy. Yes? So they're really saying which one goes to a vapor easy. Which one changes to a gas more easily? Which one goes from a liquid to a gas more easily? The answer is we are looking for the lower IMF. Strong IMFs will keep you together as a liquid. Low IMFs, those liquid molecules can go to gas easily. So we're looking for the lower IMF. Look at this molecule right here. They didn't draw it completely. You will notice, and I kind of did this on purpose, you will notice as you proceed further in chemistry that they will often leave the lone pairs off of the terminal atoms. Why? Because they're lazy. You're not ready to be lazy yet. But whoever drew this left the lone pairs off the oxygen. Why? Do the lone pairs on the terminal atoms really affect the shape? No, we're looking for lone pairs on the central atom. We're looking for lone pairs on the central atom. That's what we're looking for. This one is symmetrically shaped. This would be a linear molecule. This is symmetrical. It is linear, no lone pairs. So this oxygen's pulling, but they're pulling opposite. They're pulling equal but opposite, so they cancel. No net dipole. This one only has London. Selenium. Yes, selenium is in family 6. There are 2 oxygens on there, each preferring double bonds. So we should have a lone pair left. That's asymmetrical. Asymmetrically shaped, we're going to have a dipole. A dipole going this way and a dipole going this way, adding up to a net dipole kind of going out that direction. Leaving the selenium partial positive, the oxygen, this oxygens are partial negative. Out here, that end of the molecule is partial negative. There will be a dipole, so these will hold together easier. These not as well. In fact, you might say to yourself, what is CO2 at room temperature? Without even knowing anything on this question. Vapor means it's a gas. Has a high vapor pressure. It goes to become a gas very easily. We already know CO2 is a gas. Carbon dioxide is a gas. It's going to go to a gas easy. You're like, but I don't know anything about SCO2. If you had seconds left on the test, I would mark the one that you knew was a gas without doing anything. If you ever had seconds left. Did they give you this drawing for SCO2 on your thing? They did? Oh, they gave you the drawing. Okay, that shouldn't have been too bad. They gave you the drawing. You should have known there were dipoles on there. I didn't know they gave you that on your thing. How about on these two? This is a little rough. Why is letter B more likely a gas? Goes to a gas more easily. They both actually go to gas. There's an alcohol right here. Do you remember the alcohol group we talked about? Hydrogen on an oxygen on a carbon. When you have a carbon with an oxygen and a hydrogen on it, that's called an alcohol group. Very famous. This has hydrogen bonding. This one has the oxygen on carbons, no hydrogen bonding. Hydrogen bonding is the strongest type of dipole we can have. So they would stay together better. Are we good on that? Did that answer your question? What about the next one? 11 through 13. These are not easy. Increasing melting point means we want the one with the highest melting point last, the lowest melting point first. Yes? Is that what they mean by increasing? The highest melting point is going to have the strongest IMF. The lowest melting point is going to have the weakest IMF. So strongest last, weakest first. There we go. What questions do we have on these? This one's a little tricky. Looking at these molecules. Do we have a hydrogen on an oxygen there? That's hydrogen bonding. That's strong. So when we look at for answers, we're looking for this one last. This one only has carbons and hydrogens on it. Hydrogen's 2,1, carbon's 2,5, difference is 0.4, that's barely polar. This one has an asymmetrical fluorine. That fluorine on there is going to really increase ruin any symmetry that molecule might have. But we've got a fluorine on there. Fluorine is really strong. But how do I know the hot fluorine is not on the hydrogen? Someone might say they wrote the formula like this, C2H5F. What does that mean when they write it that way? What does that mean? The carbons are first. The carbons are first. These hydrogens are on the carbon. I know the fluorine has to be on the carbon and not the hydrogen. Why? How many bonds can hydrogen make? One. So if the hydrogen was bonded to the fluorine, it would be HF. It would be HF. You see what I'm saying? So by looking at the formula and how many bonds they want, you can rationalize that that fluorine's on the carbon, not on the H. If it was on the H, it would be hydrogen bonding. So there will be a dipole on that molecule. There will be a dipole on that molecule. That's going to be the middle one. The difference between the first one and the last one is the last one has a fluorine instead of a hydrogen. Fluorine's stronger, so that puts it in the middle. You see how we did that? Look at these molecules, H2S, H2O, H2. H2 is only London. That is the weakest London. Can you look at H2 and know it's London? It's the weakest London. It's very weak. Do you know how I did that? Can anybody explain how you know hydrogen is London, H2? With that, how do you know there's no dipole on it? Well, hydrogen's not a noble gas technically. It's in family 1, it's in the alkaline, but I don't disagree that it acts like a noble gas. Same atom, so it's symmetrical. Hydrogen here, hydrogen here. But if we subtract the two hydrogens, what's the difference in electronegativity? 0. That's going to be straight up London. So when I look for my answers, I'm looking for H2 first. That's the only one that has H2 first. It's the only one that's possible. But compare H2S to H2O. Do they both have 2 H's? Yes. What's the difference then? The oxygen, or oxygen or sulfur. Oxygen stronger, so that should be last. What about here? Do they all have borons? Yes. How many electrons does boron have? 3. How many halogens are on it? 3. Are there lone pairs left on the boron? No. So it's automatically what? Automatically symmetrical. When there's no lone pairs, it's symmetrical. It's symmetrical. So what kind of forces will be on these molecules then? Intermolecular forces, IMFs. If it's symmetrical, the only intermolecular force it can be, it's not ion because it's not charged. The only intermolecular force on a symmetrical molecule is what, please? I cannot hear you. London. I still couldn't hear you. London. London is stronger with what kind of atom? Small or large? Larger, because you have more electrons that are held less tightly. So the largest one, Bi3, should be last. The smallest one, Cl3, there is no Bf3 on this list, should be first. If it was Bf3, that would be first. BBr3 is right in the middle. That's all you have to do on those is sweep a in my flip sheet. What do we have on 14 to 16? 14 to 16. What kind of questions do we have on 14 to 16? 17. What about 18? Oh. Yes? CH4 and HF. What kind of bonding is an HF? Hydrogen bonding. CH4, carbon has four hydrogens on it, 0. That's London. Very weak. Thank you. Great question. Great question. What about the next one? Is the next one 19? Question on 19. What about 20? Nothing on 20? Why? Yes. So, ICl melts at 27. Br2 melts at -7. Let's think about the kind of forces on these molecules. Yes? I have an iodine bonded to a chlorine. Right? Iodine is 2,5. Chlorine is 3,0. The difference is 0.5. Is that polar or nonpolar? That's a polar molecule. First of all, we have different atoms on there, so it's asymmetrical. Second of all, the difference in electronegativity is a little higher. Only 0.5, but that's still a difference. There's going to be a dipole on that molecule. Br2 has no dipole. Br2 would just be London. So this has London. By the way, does this one also have London? Oh, yeah. That one also has London. So it has, every molecule has London. And in fact, iodine is on that molecule, which is a pretty big atom. So there's some good London on the one end. And there's a dipole as well. ICl is polar, which means they stick together better, which means they would have a higher melting point. What about 21? Question on 21. (21) 22. What about 22? Nothing? 23. That one wasn't too bad. Solids have to attract better. Gases don't attract very well. What about 24? The worst question on here. 24 is a horrible question. Question on it. Yes. What? Well, dipole, it has to be asymmetrically shaped, and there should be polar covalent bonds on it. BCl3 is symmetrical. Boron has 3 chlorine. That's not a possibility. Cl2 has 2 chlorine atoms. Subtract them. There's no difference in there. Eliminate that one. What about answer E? Well, the fluorine atoms are actually symmetrical. The atoms are actually symmetrical. So that fluorine, xenon would tend to cancel. Do you see why? This fluorine's pulling this way. It's square planar. That one's pulling that way. They would cancel. This one's pulling this way. This one's pulling this way. They would cancel. I hate this question, as I told you. I hate the question because this is the only one that's asymmetrical. Arsenic has how many when it starts? Roman 5 has 5. There's 3 hydrogens on there, so there's a lone pair. This is going to be trigonal or trigonal pyramidal. Why do I hate it? Because the electronegativity differences there are not substantial at all. Hydrogen's like 2-1. I feel like arsenic was like, someone look it up. What's arsenic? It's like 1, is it 1/8? 2-0. Thank you. 2-1 minus 2-0 is not a polar bond. I hate this question, as I started off by saying that. I don't feel like any of them would have a really good dipole unless I'm missing something. I wouldn't even ask a question like this. If I did, I would make sure the ones I picked there had a substantial difference. What about 26? Question on 26. 27. Let's not give up now. We can keep asking questions. 27. Here's 28. How do I know CH4 is only London? Carbon starts with 4. How many hydrogens are on it? 4. That's symmetrical. No lone pairs. That has only London. That has only London. This is 29 up there. The answer is B. Iodine is London. CCl4 is also London. Carbon starts with 4 chlorines, leaves it no lone pairs. Likes dissolve likes. London dissolves London. Polar dissolves polar. Polar can also dissolve ionic. Same thing with 30. Iodine is more soluble in carbon tetrachloride than water would be. Why? Water's polar. Hydrogen bonding. Let's just show you the answers. We will have time tomorrow to ask a few more. Tonight, if you have more questions, I'll just show you the answers so you can see them, correct them, and we will put the answer key on later today if you want to consult it again. But we will have some time to ask questions tomorrow. Tonight, we will do 6C what? 6C16. It's time to spray the desks. Again, I'll post this answer key back. I can keep showing you. For those of you that want to compare more answers, did everybody get this page? All right, then we're on our last page. If you want to compare your answers, you can, just to see how you did. Great questions today, students. 6C16 tonight. Tomorrow we'll go over 6C16 and give you a chance to wrap up any questions you have on 15.